So we continue our discussion. Uh, I guess Digvijay has already discussed about the calculation of member forces due to earthquake effects, how to calculate the member forces due to earthquake effects and using response spectrum. The response spectrum as specified in the IS code, and the formula IS code actually looks like the design spectrum is in terms of natural period, and on the x-axis it is the pseudo-spectral acceleration, and the spectrum looks like this, and it continues. It is specified up to a period of 6 seconds, and the amplification factor here is 2.5, and at 0 period it is 1. So it is normalized to the peak ground acceleration, so it should actually be called SA by PGA. So 0 period acceleration, that is the peak ground acceleration of the ground motion, is anchored to unit value. And of course there are two sets of design spectra that are specified. One is, if you will see, this linear portion is replaced by a constant flat line, right? That is to take care of the situation when you are dealing with a very stiff system with natural period less than 0.15, that is the period here, right? So if you are dealing with a system whose natural period is very small, less than 0.15, then which can be very well because of the modeling errors. You can model certain thing as a very stiff system, and then it may not actually turn out to be very stiff. So if it is if the error in estimation of natural period is because of the modeling considerations rather than the actual behavior, then you might be actually incurring much larger force than what is predicted by, or what is implied by, this linear arm of the spectrum, design spectrum. So in order to protect against that possibility of underestimating the forces, you have this flat curve for the design spectrum. In case the fundamental period is very small, smaller than 0.15, of course then the higher mode periods would be still smaller than 0.15, would be smaller still. So for that situation, it is to be used, I mean this flat curve has to be used, so there is no allowance, there is no permission to reduce the seismic force in case of very stiff systems. So you have to take care of seismic force as amplified by 2.5 times the peak ground acceleration, effective peak ground acceleration, as indicated by the zone factor. And the seismic coefficient is given by Z by 2, SA by G, and I by R. So SA by G is of course as a function of TN and damping. This design spectrum is of course specified for only 5% damping. There are scaling factors which have been provided. So for example, to find out what is the response spectrum or design spectrum ordinate of a particular natural period, for 1% damping, what you will do is you will first find out what is the ordinate, what is the spectrum value for 5% damping, and then pick up suitable scaling factor corresponding to 1% damping from the table, and then scale it up accordingly. So 1% damping, it will be scaling up. For 10% damping, it will be scaling down, right? So the scaling factors appropriately take care of that. Z by 2, this is the zone factor, and effectively represents the expected peak ground acceleration in the zone. Okay. Now let us be clear. I mean, when we are talking of peak ground acceleration, we are talking about horizontal acceleration, right? I is the importance factor. Effectively, value ranges from 1 to 2, and effectively it increases the return period. Effect is return period of design ground motion depending on criticality of the facility that is being designed, right? So for example, for a very hazardous facility containing very hazardous chemicals and all, and also the for which can have failure of which facility can have very widespread and long-term societal impacts, then the importance factor can be as large as 2. So effectively what it means is we are designing, or an importance factor of 2 is actually, I mean, you may see that it is ranging from in the range 1 to 2 for different facilities. Now that range may not appear to be very large, but effectively it is extremely it is very large. I mean, if you look at it in terms of earthquake occurrence. So intensity of ground motion changing by a factor of 2 is a very major scaling up of the excitation, and if by importance factor of 2 effectively corresponds to uh, designing the facility for the largest possible earthquake that we may probably expect to take place in that region. So obviously importance factor of 2 is reserved for facilities which can have very disastrous consequences of failure, right, which are required to be functional even during the worst possible scenario. So for example, lifeline facilities, water pipelines, oil pipelines, electrical transmission lines, and hospital facilities, public health care, community buildings, etc., the bridges, and of course the uh, storage uh, facilities for which store hazardous material like petroleum and so on. Right, so those are the facilities for which importance factor of 2 is used, and then there are gradation. You will find the typical examples of this gradation, what importance factor to be used for which kind of facility, what is proper in part 4 of 1893, that is with respect to the industrial structures. So that particular code has a very wide range of importance factor to be used for design of various components, various facilities. So you may find that in the same industrial complex, some facilities are to be designed for importance factor of 2, and some facilities are to be designed for importance factor of 1, and some other facilities for importance factor in the range between 1 and 2, so on. And R is of course what we call as the response reduction factor. So response reduction factor is as you might have already seen, it depends on the ductility and assumption of ductile behavior that is very much essential for earthquake resistance, building earthquake resilience into the system. And obviously I presume that you might have realized that how difficult it is to perform a nonlinear analysis even for a single degree freedom system. Now hopefully you can appreciate the complications that may arise when we talk about nonlinear analysis and the damage, possible damage during earthquake for a large scale facility, I mean real structural system, whole structural system, not just the single degree of freedom system. Right, so nonlinear dynamic analysis is very tricky and very time consuming, and it's not very reliable either because of various modeling assumptions and various paths that they can take depending on what is the convergence criteria. Everything might be same, but two different analysts might be using different criteria for convergence of iterations, and that may change the response trajectory completely. Right, so that is why it is extremely difficult to verify the results of nonlinear analysis, and hence it is preferred to stick to linear analysis for the design of facilities, and therefore we bring down these earthquake effects by a factor of R, which depends on available ductility, and another factor is redundancy in the system, and third one is over strength. Right, because you always provide larger capacities than what is demanded. That's the normal process of designing any facility. You estimate a demand. For example, your design calculation for a particular flexural resistance requires certain amount of reinforcing steel. Now, it is obviously not possible to provide exactly the same percentage of steel as comes out during the design calculation, because the available reinforcement bars may not exactly agree with the area of steel that needs to be provided. So obviously you will provide more than what is required. That is one source of overstrength. Another important source of overstrength is the and that is actually I would say it is of course contributing to overstrength, but it is actually detrimental to earthquake resistant design, in the sense that your material, the reinforcing bar for which it is qualified, the yield stress or the rating for which it is passed as a particular yield level, guaranteed yield, actual yield strength of that bar might be much higher. If you look at the definition of the yield strength in the code of reinforcing bar, you will find that it is not the yield, it is not the definition, the use of terminology is not that the bar yields at this level or this particular stress. It only talks of the bar should not yield at stress level lower than this, right? So what is the higher yield level, it is not specified. So obviously it is whatever bar you might be using for as a rating of 250 MPa or 415 MPa, actual yield strength might be much higher than 415 or 250, right? What is that actual strength? You don't know, right? So typically what is done is one batch of steel reinforcing bar, it is tested for 500 MPa, let's say 550 MPa, and if it fails 550 MPa, that is taken as it has passed the 415 MPa grade, and it is pushed out with the label of 415 MPa, right? And you happily use that reinforcing bar using 415 MPa, and actual yield strength might be much higher than 415, who knows. So that is the overstrength. So you might actually provide much greater steel strength capacity than what is required. So is that a good thing? Can anybody tell me, is that a good thing, having higher reinforcing yield level than what is used in the design calculation?
No, sir. No, sir. We are going for over-enforced sections.
It is for earthquake resistant design, we are going for anyway doubly reinforced beams, because it is going to be reversible in nature. So there is no single reinforced section in case of earthquake resistant design. So it is anyway over reinforced. Isn't it? Doubly reinforced sections are always over reinforced sections. So that is of course theoretically yes, it is going to be over reinforced, but not of much practical concern. Practical issues are somewhere else. The answer is right, it is not a good thing, but the reasoning is not. The correct reasoning would be, if you go back to my that demonstration of capacity design principles, capacity design concepts, we need to design for earthquake resistance or earthquake resilience uh, a system with strong column and weak beams, right? So how can I be sure that my beams are weak or weaker than the columns, and the hinging will always take place in the beams, unless I know for sure what is the yield strength of the reinforcing steel. And that is the problem. I may design a facility, I may design the complete frame using strong column and weak beam assumption, but if the actual reinforcing steel turns out to be much stronger, it is quite possible that reinforcements in the column might come from a different batch, and reinforcements in the to be used in the in the beams might come from a different batch, right? And the diameters, etc., might also be different. So there is no guarantee that the kind of overstrength that I have in the reinforcing bars that I am using in the beams, I will have the similar kind of margin available in the column reinforcements. And my assumptions, that's a very critical assumption for earthquake resistant design, that the failure, we need damage to be sustained, the building to sustain some damage during strong earthquakes, but then that damage has to be according to a designed or pre-specified failure pattern. So hinging has to take place only in the beams. Hinging should not take place. Plastic hinges should not form in the columns, right? So column capacities have to be much higher than the beam capacities. Now, how do I ensure? It's impossible to ensure that the beam capacities will always remain smaller than the column capacities, unless I know for sure that the reinforcement that I am using in the beam corresponds to the assumptions that were made during the design calculations, right? The reinforcing steel actually being used is according to the assumptions in the design. So it is extremely important that during the construction your reinforcements should be tested for failure, and if the yield strength turns out to be much higher than what is assumed in the design calculation, either the calculations have to be revised, design has to be revised, or the reinforcing steel batch has to be replaced. You cannot use the same reinforcing the same batch of reinforcement steel with much higher range of yield strength than what is assumed in the design calculations, right? Otherwise it's a catastrophe waiting to happen. You might feel that you have adhered to the design very rigorously, very religiously. All the instructions on the design have been implemented at the site, but the material itself does not conform to the design specification, and obviously the performance is not going to be according to the design, right? So depending on what is the, so this is of course that has to be taken care of during the site and construction. At the construction site, your every batch of steel has to be tested to failure and confirmed that the yield strength is not excessively high, and we are trying to impose a upper limit on the yield strength while qualification in IS codes, but obviously the steel manufacturers, I mean the code committees are dominated by steel manufacturers, and they are not really interested in imposing that upper limit, because that will increase their costing. I mean, process control has to be much more stringent, and they cannot pass off some material, some batch which has failed at 550 MPa, and without doing anything they can push that batch into market with the label of 415 MPa. They will not be able to do that subsequently. So there is a stiff resistance from the steel manufacturers lobby. So, but let us see how things pan out. It is important that in addition to the minimum guaranteed steel, we should also have an upper limit that it will not exceed the minimum guaranteed steel by a certain percentage, and then it can be taken care of in the design calculations. But until that happens, you need to be careful, because it's your professional reputation at stake. So be careful when you use reinforcing steel, what is the grade of steel that you are putting in there, and whether it corresponds to the grade of steel that was assumed in design calculations. Now secondly, the redundancy is of course your monolithic construction. I mean, for a complete collapse mechanism, you need certain plastic hinges to develop before it can the structure can be called to have failed, or turns into or loses its capacity to support the load. So higher redundancy of course is better behavior with respect to earthquake performance. And then the ductility. As I said, ductile behavior is of course very, very essential to absorb the energy that earthquake input ground motion feeds into the structure, and there is only so much that you can store by virtue of elastic strain energy. And in order to have a economical design, it is much better if some rare strong earthquakes whose occurrence is unpredictable. So if that strong earthquake occurs, then that energy can be absorbed by ductile behavior, suitable ductile behavior. I mean, without collapse, without the structure losing its capacity to support load. So ductility is important. Now, what is the importance? I mean, what is the implication? What do you mean by ductility? I have already mentioned about the importance of confinement. Confined concrete is essential, because unconfined concrete will only give you ultimate strain of 0.003 or 0.0035, around that value, right? So if you look at it, even if the yield is able to, tension steel is able to yield, the concrete is going to crush. And this is of course earthquake force is reversible. So eventually you will find that if the concrete is not properly confined and that unconfined crushing strength governs, then there is not much ductility, irrespective of what is the amount of steel that you put in. So concrete has to be able to withstand much larger strain before you can harness the large yield plateau of steel elongation in the ductility, ductile behavior. And therefore you need to have confinement, and that hoop reinforcements or the lateral ties at a much closer spacing, and that will improve the concrete behavior under confinement, and you will get, I mean, not only the concrete is able to withstand much higher strain and much higher stresses under compression, but it will also have much larger strain, ultimate strain at failure, and that is what will achieve the ductile behavior, facilitates ductile behavior. And of course, another side effect of this is, by using very high, very closely spaced lateral ties, of course our intention is to have the confining effect on the concrete, but another side effect that we get is increase of shear strength. Shear capacities are of course increased because those lateral ties help us in withstanding shear. So any chance of failure in shear is of course automatically eliminated. And as you all know, shear failure is brittle, and that has to be avoided at all costs. So confinement of concrete helps you in eliminating the possibility of shear failure. So that is another ghost that can be buried by properly confining the concrete. Now, next point that is important is, what is the issue of ductility? How it is? How do you define ductility? There are two things here that I wish to emphasize. Member ductility versus structural ductility. Right? How is it different? Let us say the easiest way to explain this is by using the notion of several linkages. There are links interconnected, and subjected to uniform pull, tension. Now let's say all of these are of steel, and one element here is of, let's say, aluminium. Right? Or let's say this material, this particular link is highly ductile compared to the other links. So whatever may be the material, right? So obviously individually the ductility level, if I look at from the force deformation curve, so this might be for let's say Fe415. Let's say this is Fe415, and maybe this is for aluminum link, right? So now obviously you can see that as you keep on increasing the load, as soon as P reaches this yield level, this material, this particular link is going to stretch. It is going to enter this plastic floor region, and the deformations are going to increase. But the forces, or of course other links, do not deform as large as by the same amount as aluminium, right? So if I look at the ductility of the total structure, this entire assembly is the total structure, total system. Aluminum link is only one element of the structure, so this element is ductile, but I am looking at what is the ductility of the total system. So I need to look at what is the overall structural performance, overall load deformation behavior of the total structural system. So you will find that usually the structural level ductility values are very, very small. You need member ductility of the order of 14 to 16 in order to get a structural ductility of the order of 2 to 3 or 2 to 4, right? Because not elements, the reason being, not all elements are going to yield simultaneously, and they are not going to flow, or they are not going to accumulate, or they are not going to admit the plastic deformation to the same extent, right? So member ductility, individual member ductility values may be very, very flattering. You may look at the single beam and confined concrete and very well detailed, and perform the analysis, the experiments and all, and you will find that it is a very, very highly ductile system, and then you say it's very, very ductile system and it should be able to do well. But the problem is, it is when the earthquake strikes, it does not look at individual member. It is the total structural system which actually participates in the seismic response, and the overall ductility at a structural level is actually very, very small. So if the member ductility is of the order of 14 or 15, that corresponds to a total structural level ductility of the order of 4 or 5, right? And that is why you will find that the largest response reduction factor for R is of the order of 5, right? So this is maximum response reduction factor that you can have is of the order of 5, and please note that this maximum response reduction factor takes into account all of these: ductility, redundancy, and overstrength, right? So that actually disguises this aspect of reality, that member ductility, a very high member ductility, does not really translate to the same level at the structural level. When we look at the structural behavior, the actual global ductility level, global ductility available in the structural system might be very, very small. But even that small ductility at the global level is very crucial in designing a feasible earthquake resistant system. So we will discuss this issue of ductility and how different types of ductility in our next lecture, and how do we account for that in design, right? So any questions?
Sir?
Yes?
Sir?
हाँ बोलिए.
Sir, what is the role of redundancy?
What is
the role of redundancy in this response reduction?
See, redundancy allows you, gives you a margin against collapse. If you have a redundant structure, then it has several modes of absorption, energy absorption, before it can be converted into a mechanism, before it loses its capacity to support loads, isn't it? So in a way it is helping in absorbing more energy. So redundancy is one way of absorption, but and that is indirectly included, accounted for in the response reduction factor. It's very difficult to quantify exactly what is the redundancy, to what extent redundancy makes up for response reduction factor. There are ranges, and that of course depends on what type of structural system are we looking at and what type of connections are we looking at. So that I mean, it becomes very ugly if we go into too many finer details. It's much simpler to realize what are the issues involved and enforce the provisions of the code correctly. Yeah, multiple load paths will be available. That's what I said. There are multiple mechanisms, and capacities, different capacities have to be exceeded, have to be completely exhausted before the structure gets converted into a mechanism, and then at that point it will stop supporting the load. Until you have a mechanism at hand, the structure will continue to support the load. The load carrying capacity might be reduced somewhat, but it will not go to zero unless the structure is reduced to a mechanism. Okay, any other question? Okay, fine. Thank you.